Never made it. Okay.
He was too late. And now he was there, and he was doing his Spanish the entire time. He was not as involved.
Supposedly.
Yeah. He was definitely listening to us as well.
Okay, well, here we go. Okay, so we are done with chapter 1.
Yeah.
Sounds better if we're done with chapter 2.
I was thinking about it, like, that sounds so sad. We just finished one.
Yeah, finish chapter 1, but it is our second chapter. So, so we are moving on to chapter 2. And chapter 2, we get to. Chapter 2 discusses more in depth at the beginning here the derivative and the tangent line problem. So chapter 2 is formally called differentiation. Chapter 1, we discussed a little bit of the differentiation as 2 points move infinitely close to each other. That's called the derivative. And then we discussed that in depth, I would say, relatively in depth, one of those days. And then we talked a bunch about limits, and then defining a limit, defining continuity, one-sided limits, defining also, or not defining, but defining the continuity, then, but a bunch of the stuff with limits. And then as we go into chapter 2 is differentiation, and initially, which is the derivative, which is essentially finding the slope along the line. So when you hear the word derivative, you think slope along a curve, instead of line, slope along a curve. So differentiation is the same idea as the derivative, and the derivative is then talking about finding the slope along a curve. So in 2.1, they say the derivative and the tangent line problem. And they have lots of different pictures and different things like that in there. And this is the thing that we've already covered on, so I'm not going to go labor intensive on the long discussion on it. But remember, we have some sort of, use a different color here, curve. And that curve, will look like this. And then they use, I'm going to use whatever variables they use for this so that we can match it. They have C and F of C for this first point, right? C and F of C. So there's your X and your Y value. And then they have another point that we find out here. And to get to that other point, rather than calling it D or L or some other value, they say you went over C to get to here, and then in the pre-calc book, do you remember what variable we used that represented the distance from C to this next point, wherever this fell? It was H. Yeah. And so we said, hey, H represents that. Now that was in the pre-calc book. I kind of like H. However, what?
Instead of delta X.
Yeah. Delta X actually makes more sense because it refers to the change in X, but delta X requires 2 symbols versus just H is 1 symbol. So I prefer H because it's 1 symbol, less cumbersome. However, delta X does make sense. And so the question is then, is if we go over to C right here, what is a way to label this point? So this is C, this point is, again, we're not going to use D, we're going to put it in terms of C. So we had to go over C,
over delta, so C plus delta.
C plus delta X. So therefore this is C plus delta X is our X value. And then our Y value is just the F of C plus delta X, right?
Yeah.
And so that's where some of this becomes cumbersome, is the notation, just with lots of variables going. But the idea is the tangent line along a curve and the slope of that. And what would be asking is, hey, what is the slope at C? And again, we've discussed that. If you're standing on a hillside, you say, whoa, this is really steep, or oh, this is really gradual, or oh, this is flat. So anywhere along some sort of curve, you're going to have some sort of slope. Now, when we do problems, we're not just looking at how steep is the slope, like of an actual hillside. But it applies to anything that we can represent by a graph. We can find slopes, which represent different things. One thing that we talked about in pre-calc was maximum problems, minimum problems, finding the minimums, and also other problems like finding the acceleration and the velocity and different things like that. So in that, we would say, though, any given point has a different slope going here. And so this point has this, if you drew a tangent line, you could represent it that, hey,
where it caresses real quick.
yeah, where it caresses real quick, you could say, hey, this is a slope of, up 1, right 2. So the slope of, if you just looked at that, you say, sure, up 1 and about right 2 to get over there. So this slope at this point is 1/2. What that would tell you on any curve, if you're thinking about it in terms of standing on a slope, you'd say, that's a pretty gradual slope. I'm going up 1 and then I'm like walking 2. That's fairly gradual. Versus here, this point would be really steep for that. Now, for the sake of just looking at this problem and figuring out, well, how do you find the slope at a point? And this is all review, but just for the sake of doing it again, if I have a point here and I said, what's the slope of the point? We say, well, I don't know, because what does the line look like, right? We don't know. So we can't just find the slope at one point, but we can find the slope between 2 points. And so we say, hey, we actually can take a point and make a secant, right? A secant is not tangent. A secant goes in between 2 points, right? Doesn't caress at 1 point. It goes in between 2 points. Yeah, so this is 2 points here. We say, okay, this slope right here, we could say, what's the slope there? We say, well, that's like up 1, right 1-ish. You're like, yeah, well, that gives you some basic idea, but is that a real good representation to what's actually happening with the slope at the curve, or at this point? We say, well, not really. And so we say, well, what happens if I move that red point farther here? Now, as the red point, if we move the red dot, this upper point, I should say, as I move it here, what we notice is delta x was way out here, whatever that change is. So we say, oh, the change from here to here is big. Big's a relative term. But as I move the delta x, as I move that change in x to here, between here and here, it's getting not bigger, it's getting smaller. And then as I move the point to here, my delta x is getting even smaller, and then it's getting even smaller and smaller and smaller. And so if delta x started at whatever, 10 units away, it goes to, we can do it in halves, it's going to, 5 units to 2.5 units. I should have picked even number to get from like 8 to 4 to 2 to 1 to 1/2 to 1/4 to 1/8 to, what is it going towards? As it's moving this direction, as you keep moving this closer and closer, it's going to 0. So we're saying delta x is actually going towards 0. It'll never hit 0, but it goes infinitely close to 0. And that is where all of chapter 1, what were we working on? We were working on limits. Yeah, and so that's this whole concept. Yeah, lots of limits. So in this case, we're saying, hey, what is the slope between this dot and this dot as this dot moves infinitely close? And to find slope, you use your slope equation. Well, what's our general slope equation?
y2 minus y1 over x2 minus.
Yeah, so your slope is y2 minus y1 over x2 minus x1, okay? Well, we're saying, what is the slope for calculus? What's the slope along a curve? So we need 2 points. With those 2 points, one of them is going to stay fixed, the other point is going to be moving. And so how do we represent that? Because we say, well, yeah, it sounds good. Y2 is this, but we know that Y2 was here, but now Y2 is here, then it's moving. How do I say, well, X2, X2 is out here, but it's moving all the way here. So we use this concept of the slope is the limit okay, as, remember, this point is going to stay the same, this point is going to move, but what's moving on this point? Remember, C is staying same, but what's going to move? Delta x, right? So we're going to say the limit as delta x approaches 0 of my slope equation, which is, and do you remember seeing some of these problems, right? F of x plus delta x, or in this case we're using the variable c, minus f of c, and if you had this point be x instead of c, that's fine, or you could have it be z or something like that. Maybe they use c because it's not x, so you have a little bit less than x and delta x, too many x's going. So, so here, this is going to be c plus delta x minus your x value of c. Now the book notation is generally not going to give that to you on the bottom. What are they going to write on the bottom?
Delta x.
Yeah, just delta x, which is your change in your x, which makes sense because 2x subtracted is going to be delta x, which is change in x. Now the issue is that I like showing this in the beginning because it emphasizes x2 minus x1. It's just that c is going to cancel. Okay, so this would be the limit. Now they have in the book, if you're looking at it, they have m, just to match their notation, they have m sub sec. Well, what does m stand for? M stands for slope. Sec stands for secant, right? Now, they actually, on page 97, I didn't, I kind of jumped ahead. So sorry, on page 97, they go like this. They eliminated this, and they say the slope of the secant, meaning between here and here, it's stagnant. Then, as soon as you tack on the limit as delta x approaches 0, now, it is technically a secant because it's 2 points, but because they come infinitely close, mathematically, we would drop the secant. It's just the slope at a given point, because mathematically they become infinitely close. And so, with that being said, you're going to see like a definition on the bottom of page 97. It says, definition of a tangent line with slope m, so there we go, slope m, is and their initial thing, which you don't, we can write just so that we see it, is delta x approaching 0 of delta y over delta x. Now remember that delta just means changing. So this is just our slope equation. We've referenced that since algebra 1, and it's slope of y over slope of x. We're changing y over changing x. And then they write this thing right here, and that's our limit with the limit definition in there, and then that is equal to m. That is called the tangent line. That is also known as our derivative. Now they have later on page 99, they give the definition of the derivative of a function. So then they have, so this is the limit, this is the slope of a point that is tangent to a curve. Here's your definition. The derivative, definition of the derivative of a function, derivative of a function. So now you have a function, f of x is your function. It says the derivative is, they have this notation, so your function's f of x, and then they have this, and then they just have limit as delta x approaches 0, okay? But then what they change it to is f of x plus, like our original definition that we were seeing, where they just have a general x instead of using the variable c, okay? We were using the variable c because we were saying in this specific example it is at this value of c. Here they formalize it with a general definition of any value of x. Now, so it's the same thing. So if you look at this definition of a derivative of a function and this definition of the slope of a point that's tangent to a curve, they're the exact same thing. They just change a variable c. Now, this notation, this is called f not first power, not f inverse. If you remember inverse, That's f to the negative 1, but it's not a negative exponent, it just represents inverse. So this is called f prime. Okay, so when you say that, you don't say, you could say f, the derivative of f of x, yes, that gives it away that it's a derivative, but it is f what we would call prime of x. Now they give also on that page 99, they give several different things of notation things. So this is a definition you'll need to know. We will, in chapter 2, get into all of our cheater methods. I believe in chapter 2, get into our cheater methods of the power rule, the quotient rule, product rule, where we actually transition away from using the long slope definition, but this will be used like at least one problem on the mid-chapter assessment and the test to say, hey, I do understand that it's slope between 2 points moving infinitely close to each other. So that's important.
It's straightforward, I feel like. So.
Yeah, it is. It's very straightforward. That's why, and obviously, as you've experienced a little bit, like calculus, the problems maybe get longer, there can be challenging ones, but it's back to algebra 1. It really is. Now, I think the hardest part is you're not looking at y2 minus y1, you're looking at f of x plus delta x minus f of x. As the limit of delta x approaches 0, it's like, that's a lot of letters, but it's really it's just the slope.
The same,
yeah. Then one of the things that threw me off for years, actually a year of calculus, maybe even longer, was the notation. Now I remember when calculus was being discovered, it was being discovered all over the world by different people with different notations and people. There wasn't a universal understanding of mathematics. Like, hey, standard form. Why is it standard form? Well, it became standard form through the process of everybody inputting ideas, and now we have standard form, ax plus by equals c. Even in that, there's some variation of, is it negative ax, or can it be a positive, always have to be positive ax, So notation-wise, there was this, how do we represent the derivative? Because it's obviously, we can't just say f of x, because that's just the function. We want to define, we're finding the slope of this curve. Now, when you do, and keep in mind, the slope of a curve, we will be able to come up with general slope equations for an entire curve. So even though the curve is going to have, you just come back over here, the curve is going to have a different slope here compared to here compared to here, we'll be able to come up with a general slope equation that allows just plug in for x and it gives you the slope. Plug in for x gives the slope at any point along there. Or we can find the slope at any specific spot, doing it at a specific spot. We'll do some examples. But this represents the slope of a curve at any given point. So then if I said, can I give you, this is a side note. Okay. If I said f prime of x is equal to 2x plus 5, what form does that look like?
I was saying the wrong one. Wait. No, is it point? No, point.
Slope intercept form.
Yeah. I always want to say point, so I was the wrong one.
Yeah, so slope intercept form. What's the slope on that? 2. So in other words, this is the derivative. So if I said, what is the derivative? I mean, this is my function. Actually, maybe that was poor to do that. Let me just erase that. That's my function. If I said, what is the derivative? Derivative means what is the slope? F prime, what is the slope? You're asking, what is the slope of this function? Well, what's the slope of this function? 2. So f prime of x is equal to 2 every time. So f prime of x says, hey, what's the slope of my curve or my line? You don't have to be using a curve, you could be using a line, which we can identify with algebra what the slope is. We memorize that. So notation-wise, though, this says, hey, what's the slope? And then other notations go in order. They have dy dx. That represents the exact same thing. Okay, so dy dx. What that would be emphasizing is not the function notation. It's just representing you have the change in y over the change in x, which would be the slope, right? Then you have other notations, which you sometimes see. These two are probably the most common, I would say. Then you have other notations, say d dx of f of x, like that. what that notation is emphasizing is, it is emphasizing a slope, d dx, of a function, f of x. Little cumbersome compared to just f prime of x. But you'd be emphasizing, this is my idea of my change in f of x over change in x. The same way this could be written as d dx with y on the outside. You could just look at it different. So you're like, oh yeah, the slope of a function y or an equation y, rather than saying just the, like this is simply y2 minus y1. It's, you're finding the slope of a function, and then with the idea that it is a change in y over change in x. And then the other notation you might see, I don't see this very often, but capital D sub x of y. I don't see that one very often, but you could see that one. Okay. So those are notations. They all represent the exact same thing, or what the process that you're going to do. So for years it was like I thought this was different than this, but you know, it's the exact same thing. So it was probably my error that I didn't take the time to figure out that they're the same thing. And then later we'll actually do equations with this where you know your change in x actually. And so then what you'll do is you'll bring that over like a variable, its own variable, bring it over to the right hand side, so then you're solving for dy, the derivative of y or the change in y, and you already know your change in x, so you're bringing that over, you can actually move it back and forth. So that's why that notation gets used quite a bit, because you can separate this and this depending on the information given. Okay, so then okay, this one comes up a little bit. The page 101, if we look over there, I'll draw this on the board for us. But it says differentiability and continuity right there at the top of page 101. And so what they have here is they say, hey, there's an alternate form of the derivative, and they show you this. So this is the alternate form of the derivative. F prime of c is equal to the limit as x approaches c of f of x minus f of c all over x minus c. So then, and that looks like a derivative because you're finding the slope, right? So even if you're finding the slope of a line, it's still the derivative. We just don't call it a derivative in Algebra 1, we call it finding the slope of the line. But you can say, okay, y2 minus y1 over x2 minus x1. And this is if you look at the picture, this would be, they have this picture drawn, I'll kind of match what they have going there. But they have a point here, and then they have a point up here. This point here is C. This point here they label as X. So they give it a specific, well, it's not a value, but they give it a variable X. Versus like over on this picture, we are just saying this doesn't have a value like X or Z or T, it's just some change in X. So what this does is this allows us to look at going to a specific point here, and we say, okay, this is C, comma, f of c, right? And then this is over x up f of x. So it's y2 minus y1, got it, over x2 minus x1, got it. But we need a limit process that moves the points infinitely close, and they're going to take x and they're going to move it close to c. And so what they're saying is that, you know, x, if you will, you can think of it as x approaching 0, because the x value is getting smaller, but they're saying that you're going to look at it in terms of x is approaching c. So if c was over 3 and x was over 5, you would actually be saying that 5 is not going to 0, because you're not talking about the change in x, but x is going to be getting closer as it moves. It goes to 4, then to, you know, 3.8, and then 3.2, and it's getting infinitely close to 3. So, which means your x values are getting infinitely close to each other. So, same concept you'll see some problems like that. So that's what that is meaning. You're not talking about the value going to 0 anymore, you're talking about the value going to the other value. So, and we've done limits like that, right? So saying, hey, as x is approaching 3, this notation, by the way, you would not say as 5 is approaching 3, you won't see that. It'll be a value of like 3, and then x is unknown, and you're moving it towards 3. So that's the alternate definition. Okay, homework-wise, I thought I had printed these, but apparently I have it on my list to do. Let me get you just some problems to get started. I know there's nothing due tomorrow, but that way you can have some stuff you can be looking at and study hall or something if you chapter 2 and homework K. Maybe I should send it to the group chat.
That we used to do.
I'll do that, but yeah, because it's like 1, 2, and then 5 through 43 odd, and then a handful of other ones. So I'll write it up here for 1, 2, 5 through 43 odd. I'll get the rest to you. That would get you started on it if you wanted to try a couple problems tonight. And then we'll start looking at examples and stuff tomorrow. But and there's more to it. I'll get those sheets printed. And then I'll just send it to the group chat. Is it beneficial to have a digital copy of it?
Yes.